Welcome to our presentation on Web-Based Structural Identifiability Analyzer presented for Maple Conference. My name is Ilya Ilmer, and today I will tell you about this new web-based tool that we developed entirely in Maple to solve the structural identifiability problem. In this presentation, we're going to go through the definition of the identifiability problem and some of the representing examples. We're going to go over some of the existing algorithms, and finally we'll introduce the structural identifiability toolbox. We'll finalize the presentation with some comments on the future direction and some of the current bottlenecks that need to be resolved. The identifiability problem arises when we are faced with an ODE model of a real-world phenomenon, and we would like to know whether a parameter value could be recovered from the model's data. The structural identifiability is a theoretical property that can help us answer these questions. We say that a parameter is locally identifiable if we can determine it up to finitely many values. If such a parameter can be determined uniquely, then we say that it's globally identifiable. If neither of those is the case, then we say that a parameter is non-identifiable. In that case, we might be interested in finding functions of that parameter, or combinations of parameters that are identifiable and solve the issue of non-identifiability. So let us consider some of the representative examples. In this first example, we have a simple system with one ordinary differential equation, one initial condition, and one output function. This output function can be considered as something that's being measured in the lab. Parameters c and k are complex-valued constant parameters. So we're interested in finding whether or not these are identifiable. It is clear that the solution to the system is a linear function of time, and since we see that output function is just x itself, then we can determine what y of t equals to. Now we assume that measurements are done continuously and there are no measurement errors involved. Given that information, we can see that parameter c is locally identifiable because we only know c squared. Now at the same time, parameter k is globally identifiable because it is just a measurement at time 0. In this next example, consider the following system with a single differential equation x prime equals 0 and two output functions. We do not have initial conditions here, but the same parameters c and k, which are complex-valued constant parameters, are still present. Notice that none of the parameters are identifiable, because the solution to this equation is a trivial constant value, the value at the time 0. And given the two output functions, we only can have one equation with two unknowns, c and k. Notice that if we take the original system and make a structurally identical copy of it with the same kind of output functions but different indices, then we will obtain two equations with two unknowns which can be solved. So in this case, introducing an extra copy of the input helps us resolve the non-identifiability of a parameter. Now let us go over some of the existing approaches. Currently, there are several tools out there that solve identifiability problems, and all of them rely on different things. There are tools that can be grouped into what's called a series-based approach, for example, GenSSI. There are differential-based approaches such as Combos and Daisy, and there are programs that determine identifiable combinations and multi-experiment identifiability. Combos is actually one of the programs that looks for identifiable combinations of parameters. So you can see that there are many different options, and quite a few of them may require non-trivial installation steps and maybe not be available. They may not be available to all systems. So to address the need for a unifying tool that does not depend on the user's computer system and availability of software, something that can be accessible from all devices, Maple introduces a service called Maple Cloud where we can host our applications for free and they don't require installation. You can follow this link or this QR code to visit the web page of the application. In a minute or so, we're going to see the details of the toolbox in this video. This program utilizes implementations of some of the recent algorithms that deal with both individual parameter identifiability and identifiability of parameter combinations and multi-experiment identifiability, as we saw in the example earlier. This program is implemented entirely in Maple and is hosted on the Maple Cloud service. So this is the main page of our application. It begins with a short README that lists citations of the underlying algorithms of the application and links to the GitHub repositories that host the original code. So we're going to close it for now. We're building an FAQ section, which could be expanded by various questions from users that we receive. I listed my email over here, so everyone who has a question can contact me if necessary. Next, we observe the input window. So this is where we control everything that happens under the hood of the application, or as much as we can rather. We provide several built-in examples. So in this case, we're going to look at something called the slow-fast, the system of ordinary differential equations taken from this paper. We provide two sets of settings and two sets of description corresponding to each track of the application. Here we list several warnings and necessary notes and tricks that could be done to improve the workflow for the user. We're going to close them for now, and I'm going to walk you through each part of each track. So in the individual parameter identifiability track, we have the option to print the number of solutions. We can specify the probability of correctness. Here it's defaulted to 0.99. We may need a lower probability of correctness if we desire a faster runtime, or if the runtime is not a problem, we may wish to increase the probability of correctness. We can specify parameters, which will be parsed by Maple's parsing functionality. These parameters will be used to check identifiability, and we can specify the number of experiments. This is the copies of this input system that will go into the application. We accept two forms of input. One is text-based, one is Maple functions-based. So this one is actual Maple syntax, can be comma separated or semicolon separated. We use string tools to parse input that is text-based, and we use that by default so that it's more open to users who are not familiar with Maple syntax. We allow the user to speed up the computation of individual parameter identifiability track. If we turn on this functionality, there is no longer probabilistic guarantee because we're now using a fixed positive characteristic when computing Grobner basis, on which this application relies significantly in the individual parameter identifiability track. We're going to turn on the identifiable combination functionality, and we're going to walk through all of the options in here. The first option we see is we can attempt to bypass using cyan. This is going to use an attempt to use the output from here to shorten up the runtime of this part. For example, if everything here is reported as globally identifiable, there's no need to run these computations because we can guarantee with probability 0.99 that the results are going to be the same. This can significantly improve runtime for various examples, and one example will be this chemical reaction network. So the runtime without bypass of this part of the application can be up to 400 CPU seconds. With the bypass, it is extremely fast. Next, we have the option to, first of all, simplify the combinations. This is just for visual presentation. It performs algebraic operations to simplify the representation of identifiable combinations for the user. You can also turn off the single experiment identifiability check so that we only focus on multi-experiment identifiability check. This part tries to refine the bound determined for multi-experiment identifiability check. We can also turn off computation of the bound entirely for all programs. If we click on the determine button, we're going to observe two things. The dial here that indicates whether a program is running or not is going to move to 100, meaning that it's running, and we're going to see a progress log over here, and the final outputs are going to be presented on the bottom. We're going to present the individual parameter identifiability results with solutions per parameter, number of solutions per parameter. Then we're going to present the identifiable combinations results, the respective runtime of each track, and the detailed logs of each track. So let me click on determine. So as you can see, we have the bound of 3 and the single and multi-experiment identifiability checks finished. We see that some parameters are identifiable and others are only locally identifiable. And we see that global identifiable parameters have unique solution. Now let us turn on the refining of the bound and run this again. So we're going to actually clear the log. So as you can see, now everything is cleared. Now let us run the computation again. As you can see, the bound is being refined, and it went from 3 to 2, which is great because it means that we don't need to perform 3 experiments and we can perform only 2, or at most 2. Let us incorporate this into the individual parameter identifiability track. So we're now going to use 2 copies of the input. Note that this would mean that there will be copies of initial conditions. For that reason, initial conditions will not be present in the output anymore. So we're going to click determine. We're going to run the program. As you can see, there's no output for identifiable combinations anymore while this is turned on. But recall that there's a bypass. So the bypass is actually going to take this result and report it in here. So from what we've just seen, there is now a fast and readily available identifiability analysis tool that does not require any installations. We were able to minimize the overhead of individual parameter identifiability solution so that we could use that information to accelerate finding identifiable combinations. Notice that this was not done before in the algorithms that were used in the application on their own. So the combination of the 2 approaches really makes the difference. We compute the characteristic sets for the identifiable combination problem using differential algebra package of Maple. However, this is still somewhat of a bottleneck because there's a memory limitation in using this package. We're currently exploring the option of using differential Thomas decomposition to find characteristic sets in hopes that we will be able to resolve the computational problem of memory limit. Thank you very much.